Hi, everybody. I'm MariaGorinova from University of Edinburgh. Firstly, I just want to say thank you to the STAN organizing committee, StanCon organizing committee for switching my talk. I really appreciate it. Thank you about that. So today I'll talk about the slightly less intensely constrained version of STAN called SlickSTAN, which demonstrates that STAN's program blocks are not necessarily an essential part of the model. The main motivation of this research is really to show that program analysis and programming language techniques can be applied to existing probabilistic programming languages, including STAN, in order to aid probabilistic inference. Right, so surely there is no need to spend much time introducing STAN to you. But I just want to gloss over the most important bit of for this talk, which is the program block. So if we ignore the functions block for a while, a STAN program consists of 6 blocks, each of which appears in order, and they can access variables that are declared in previous blocks. And only one of them is compulsory, the model block. Right, so as I said, SlickSTAN doesn't have any program blocks. And why, you might think, why did we think that this is a good idea to get rid of the program blocks? And there are several reasons. So the first one is that this block syntax makes it difficult to think of STAN programs as a composition of other STAN programs. And you might wonder why that's really a problem. Well, if our language is compositional, then it's much easier to do changes to the program, to go ahead and make a change or like add something new and so on. And secondly, well, STAN is awesome, right? Like this conference is an absolute proof for this. There are so many people that do so many interesting things with STAN. Now imagine how much more powerful it would be if it's easy to write new functions and new libraries in STAN for STAN. And if the language is more compositional, that it will be easier to be able to do something like this. This is also connected to the second point in this slide. User-defined functions in STAN are inflexible in the sense that we can't, for example, define new parameters inside a function. All the parameters need to appear in the program block. And finally, how do we really decide where to declare a variable in a STAN program? How do we decide in what block to put it in? So for example, going back to this slide, we could have put the generated quantity variance y into the transform parameters, and that will be an equivalent STAN program. But it will run slower because of the way inference in STAN works. So in order to optimize our programs, we need to know how programs are executed in a way. Right, so what is SlickSTAN? SlickSTAN is a blockless version of STAN. The only information we give regarding what block a variable belongs to is what's our data. So you can see the data keyword over there. But that doesn't have to happen in the beginning of the program. That can happen in any order. So we have interleaving statements. Some of them declare data, some of them declare parameters, transform parameters, and so on. As long as the statement doesn't reference a variable that is not declared previously, this is a valid statement in SlickSTAN. So what's currently implemented is a compiler from SlickSTAN to STAN, which takes a program like that and in a way shreds it into STAN blocks. And this is, why do we want to do this again? Well, you can see that in this way we can keep declarations and definitions of variables that are related to each other, close to each other, unlike here where we are forced to have, for example, sigma y in transform parameters and then use it only here in model. Another important reason for removing the blocks is user-defined functions. And this is an example taken from the Stan manual where in order to be able to explore the neck of this funnel well, we don't want to directly model X as having standard deviation depending on Y, but we want to instead work with the parameter X raw and then get the transform parameter X from it. Now it makes sense to have a function that does this reparameterization for us, this non-centering reparameterization. But this is not possible in Stan because in order to do so, we have to have a local parameter inside a function, namely X raw. In Slick Stan, that's possible, and here is how the program works. So it's a completely standard definition of a function. Now, how does Slick Stan do all of this? Well, it uses something called information flow analysis, and this is what information flow is really. So information flow is a transfer of information from one variable to another. Here in the first line, we have information flowing from X to Y. In the second line, we also have information flowing from X to Y, though, because if we know that Y is 0, then X must have been smaller than or equal to 5. Information flow analysis is used a lot in the security community, where you want to prevent secret information leaking to the public. So if we have two variables, one of them is of level, that's what we call them, level public, and the other one is of level secret, then we want to allow for the secret variable to depend on the public variable. That's perfectly fine. Secret information depends on public information, but we want to disallow public variables depending on secret variables. So those two statements should be invalid in our language. Information flow in Stan is slightly different. So going back to the blocks, we can see that the information flows from the data block down to the generated quantities block. And grouping the blocks together, we identify three level types, and those are data, model, and generated quantity, with data and transform data being a level data, parameters, transform parameters, and model of level model, and generated quantities is the only block of level genquant. Now, the key idea of Slick Stan is to use, to define some set of rules so that we can infer what the level of each variable is. So we want to have things like that. For example, if a variable is declared with the keyword data, then it must be of level data. If it's not declared with the level data and it's never defined, so that's what this not equals here means, then we want it to be of at least level model. So all the data must be declared with the keyword data. And then if X depends on Y, then we want the level of X to be greater than that or equal to that of Y, and so on. The problem is that following those rules to figure out what the level types must be, we have they're not unique. We figure out that we have different ways of assigning those. So how do we choose one? Well, if we go to Stan's manual, we can see that different statements from different blocks are executed in different places. So, for instance, the transform data processing happens before we start sampling, while the generated quantities are executed only once per sample, and transform parameters once per leapfrog, which is many times per sample. So that means that it's most efficient to have something at level data and least efficient to have it at level model. And we use this, which we call the performance ordering, to pick the most efficient assignment of levels to variables. Right, so yeah, this slide states this again. Now, having inferred what each level is for variables in SlickStan, we need to do, unfortunately, one more step, which is elaboration step. So this is needed because functions in SlickStan are can do more things than the functions in Stan. So we have to to translate to Stan, we have to statically unroll those. So take the call to the function and actually substitute it with the body of the function and so on. After this, translating to Stan is easy because, as you saw, the syntax of SlickStan is very similar to that of Stan. All right, so that's again the example from before and how it will be translated to Stan. So firstly, we figure out what the level types for each variable is. So you can see that the constants alpha and beta are of level data, and then we have the parameters, the parameter mu I, for instance, of level model, and so on. And now, knowing this, we can shred into a Stan program. So again, we have alpha and beta being of level data, but they are also assigned to, which means that they have to be transformed data rather than data. We have sigma y, which is of level model, but has been assigned to, so it has to be transformed parameter rather than parameter, and so on. And really, that's what we have currently. And a couple of words about what our plans for future work are. Firstly, currently, user-defined functions can't be vectorized. So what I mean by that, you know how Stan really supports what in Python is called broadcasting. So we can have a function that it's normally works on scalars and put a vector in it instead. So with user-defined functions in SlickStan, that's not possible, but if it were possible, that would increase usability even more. Another idea is to use type inference the same way we use type inference to deduce those type levels I showed. Use it instead to figure out what constraints on variables are automatically. So for example, if we used a variable as variance somewhere in our program, we want to constrain it to be positive. So instead of having to explicitly specify this. Finally, formalizing the semantics of Stan. What do I mean by that? Well, really formally saying what a Stan program means. If we do something like that, then it will be easier to implement semantic preserving transformations. So take a program that might not be very efficient, but knowing what its meaning is, transform it into another program which is equivalent semantically, but it's, say, more efficient. And that's it. Thank you very much. And you can see more about SlickStan on this page from the previous conference. Thanks.
Okay, questions?
I'm in front. I always get the first question. This is super amazing. Thank you so much for this presentation. If I have a maybe kind of out there question, but if you ask Mike Betancourt why Stan can't support sparse automatic differentiation Hessians, he says it's because Stan is a procedural language, and so you can't guarantee that the model is a directed acyclic graph. But a lot of Stan models are actually pretty simple, and they are directed acyclic graphs. And I was wondering if you could use this similar kind of analysis to detect DAG structure in models, declare that structure to Stan, and then we can get sparse Hessians too. I know in generality it's probably too hard to do, but in a lot of simple cases, maybe you could do like a very similar analysis to just kind of break all of the parameters up into levels and then make that into a DAG and then get sparse Hessians. Does my question make sense?
I think so, although I have no idea what that thing that you want to implement is, I must say. Yes, the answer is yes. I think it is possible to, especially if the semantics is formally defined, then it is possible to kind of analyze the program in advance to figure out what the structure is and if something like what you're saying is possible, but I'm not entirely sure.
You mentioned briefly this example of Neal's funnel and how you could automatically do that reparameterization. Could you talk a little bit more about how that works, if that's something you have to, that SlickStan automatically does, or you have to define another function that can operate on the code to do that?
Is that the example you mean?
Yep.
Yeah. So you have to define the function, right? So this is the SlickStan program. Oh, you mean Stan? Or, sorry.
So, yeah, I guess if you're in SlickStan and you want to declare a model, you want to either to use the centered or non-centered parameterization.
Yeah, well.
How does SlickStan know how to make that transformation of the program from the centered to non-centered?
Well, it's not automatic. So you have to see, for example, here you actually said instead of x twiddles normal something, you said x equals non-centered _ normal. So that's actually calling the non-centered reparameterization function that you defined above. Is it?
So that's kind of then it like inlines that function, or
So it's defined there. I don't know if is that visible? No, because Stan functions don't support this. So this involves defining a new parameter, declaring a new parameter. So inside of NC _ normal, you declare the parameter x row. So this can't happen with a function in Stan, as far as I know.
Hi. So just to kind of comment on the first question that was asked regarding transforming Stan's analysis into DAGs. So I do know that PyMC3 is already doing that kind of work. So DAGs are directed at cyclic graphs. And so, I mean, I don't know if there are plans, I haven't heard of these, but the plans to kind of, I mean, it sounds like there aren't based on what the first person said, but, I feel like Stan and PyMC3 are sort of like the big players out there in terms of probabilistic programming language. This isn't really a question, it's more like a comment, to follow up on what the first person asked, but just to let you know that there are things out there that are already sort of doing what you are requesting.
Other questions?
So glad we had time. Trying to let other people ask questions. So there's two other places. I was expecting Ryan to ask a different question, because I'm asking a question now on his behalf, which is, can we postpone making the data non-data decision? Because that lets us implement a bunch of algorithms that we're thinking about now. So our variational inference algorithms, max marginal likelihood, a bunch of robustness stuff that Ryan's doing for sensitivity of priors, would be really helpful if we could do the kind of bugs and jags trick of waiting till runtime to see what's data or not. It's going to require a recompilation, at least in Stan the way it's currently written, but I think you could probably do that here. And there's a second part to this question, which I think you can do that with the transform parameters versus parameters. The only thing that's different between, transform parameters and local variables and model blocks is whether they're saved. And somehow that's a decision that really seems like it should be on the outside, not really part of the model. Mm-hmm. So it seems like with this formulation, you have the flexibility to make it pretty easy from the outside to control what gets saved and to control what's data or not.
Yeah, so I think currently the way it works, you can't postpone it because it is translated to Stan. So you need to decide if You want to put it in the data block or in the parameters block and so on. But otherwise, I don't see why not, because this analysis can give you a set of levels at which each variable can be, rather than just one. So yeah, I think it's possible to.
A rather sort of naive and simple question, but follows on a bit from what Bob was saying, is it worth simplifying the terminology as well? Because I find parameters very confusing when I'm teaching this to biologists, because I keep on saying that in Bayesian everything has a probability distribution, and we only differentiate between an observed and an unobserved variable. Whether, if you're dealing with missing data, which is stuff that I work on a lot, you have to treat it as a parameter. And I don't know, I think SlickStan is sort of like the start for that, because you don't have to differentiate between, calling it a parameter, rather than it's either observed or unobserved, and then you just give it a probability distribution.
Yeah, I'm not sure which part of this was a question, but yeah, I agree with what you're saying.
I don't know whether it makes sense to actually call these unobserved and observed if we're going to sort of formalizing semantics, as you were saying earlier.
Mm-hmm. Well, I don't know, because in a way I was thinking of the data block as observed variables and the parameters block as unobserved variables, if that makes sense. But maybe we can talk afterwards, because I'm not sure I understood what you mean.
Okay, so let's thank Maria,